What's up, guys? It's me, Sir Ernest, and today we're going to discuss a sample problem involving forces between dipoles and point charges. So the problem reads, a dipole P is a distance r from a point charge Q and oriented so that P makes an angle theta with the vector r from Q to P. The question is, what is the force on the dipole? And letter B, what is the force on our charge? Okay, so first, again, let's try to illustrate the problem at hand. So for example, we have a charge here. So this charge produces an electric field. So let's say at this point. Okay, so the electric field at this point, let's call this point script P. Okay, and this is our charge Q. Now, at point P, this is where our dipole moment is located. So let's say this is your dipole moment. And that dipole moment is R away from Q. So this is R. Okay. So in general, this dipole moment, or P, makes an angle theta with respect to the vector R. This is your vector R. This is the line along vector R. This is theta. Okay. So on the other hand, so let's say we have a reverse or reverse situation wherein, example, this is your P, or your dipole. It is located here, and then let's say this is point Q. Okay, so if you're going to call the position of Q with respect to P, we have, let's call that R prime. So here we note that R is just the negative of R prime. Okay, so let's take note of that. Now at point Q, we have our charge small q. Okay, so in this manner, we can define two unit vectors. In this case, we can define our unit vectors R hat in this manner. And then this is R hat. Let's call this R hat prime. So R is equal to negative, R hat is equal to negative R hat prime. Okay, so the goal is, for both A and B, is let's first calculate the electric field at points P and at point Q. And then, using this equation, the electrostatic force on any charged particle, or on a charge, which is equal to Q E. Now for a force on your dipole moment, from our previous discussion, that force is equal to P dot the del operator times the electric field. Okay, so this is the force on a dipole, while this is the force on your charge. Okay, so let's focus ourselves first in letter A. Okay, so for letter A, the force on a dipole is given by this equation, where P is the dipole moment, and E is the electric field due to a source charge. In this case, that's Q. Okay, so if we're going to calculate our electric field due to the charge Q, Coulomb's law says this electric field is equal to 1 over 4 pi epsilon sub 0 times Q over R squared R hat. Or in terms of this vector R, we have Q over 4 pi epsilon sub 0 times R vector over R cube. Because remember that R hat is equal to R vector over R. So this is R vector over R times 1 over R squared is R vector over R cube, which is equal to X hat plus Y hat plus Z hat divided by the magnitude of R, which is X squared plus Y squared plus Z squared to the 1/2. Okay, so that means this electric field is now written as Q over 4 pi epsilon sub 0 times X hat plus Y hat plus Z hat divided by cube of this, because this is R cube. So this is R squared plus Y squared plus Z squared to the 3/2. Okay, so therefore the electric force on our dipole, let's call this FQ, because Q tells you the source of that electric field, or the thing that acts on your dipole. So that's called this FQ, and this is equal to P dot del times E. We know that P is given by P dot del is just P x times derivative with respect to x plus P y times derivative of derivative with respect to y plus PZ times derivative with respect to z. So this whole term is actually an operator, and this operates to your vector E. Okay? So again, as I mentioned, this operator is not, while del is an operator, the fact that you're going to take the dot product between these two vector, a vector and an vector operator, this is this results into a scalar operator. That means this is a scalar operator, and it needs to act on something, and in this case we need to this acts on our electric field, and that electric field is this. Okay, so this acts on Q over 4 pi epsilon naught times x hat plus y hat plus z hat divided by x squared plus y squared plus z squared to the 3/2. Okay, so as you will notice here, this is a scalar, this is a scalar, the denominator is a scalar, And they're all common to x hat, y hat, and z hat. So what does it mean? It means that this whole thing will act on x, will act on y, will act on z as a vector. Okay? Now to make it a little bit clearer, we can actually solve based on this equation. Sorry about that. The x, y, and z components of this vector. Okay, so let's do it to make it a little bit more clearer. Okay, so the x component of f, which is fx, can now be written as follows. Of course, this whole thing will act on this thing. Okay, so this is q over 4 pi epsilon naught times px derivative with respect to x plus py derivative with respect to y plus pz derivative with respect to z. And then this acts on x divided by x squared plus y squared plus z squared to the 3 halves. Okay, you follow? So what I did here is I factored out this constant, and then I allowed this to act on the 3 components. So the first component of this vector is x over this thing. Okay, and we do the same for y and z later. Okay, so this involves 3 operations: partial derivative with respect to x, with respect to y, and respect to z. Sorry, I'm just adjusting the lighting. Allow me to adjust the light. And I think this is okay. See it now? Okay. Okay. Okay, let's continue. So let's start with the first term. First term. This term applied to this. So this is p x derivative with respect to x. It's x over x squared plus y squared plus c squared to the 3 halves. Okay, so this operation is with respect to x, so the numerator and denominator are both functions of x. So therefore, we use quotient rule, or we may also use product rule. Okay, so let's do it. So this is px times, copy the denominator. So that's low d high plus high d low, minus high d low. Okay, so low is 1 over x squared plus y squared plus z squared to the 3 halves times derivative of the numerator, which is 1, minus high is x times derivative of low. So this is 3/2 times 2x over x squared plus y squared plus z squared to the 5/2. Okay, you follow? So as you notice, this will cancel. Okay, so right now I know it's tempting to combine the two x's here to make it x squared, but for a moment let's just say these two x's are separated so that later we will see some kind of a pattern. Okay, so let's simplify this. So this, you can do the simplification later, and this is simplified to be px times 1 over r cubed minus 3x times x over r to the 5th. Okay, here we take note again that r is x squared plus y squared plus c squared to the 1/2. Okay, so this is our first term. The second term is py py times derivative with respect to x, with respect to y, sorry, with respect to y of x divided by x squared plus y squared plus c squared to the 3/2. Okay, because this is with respect to x, the numerator will be considered as a constant. Okay, so this is pyx times the derivative of the numerator. So that is negative 3/2 times 1 over x squared plus y squared plus z squared to the 5/2 times 2y, which can be written as, again, we just do the differentiation and we end up with negative py times 3x y to the r the 5th. Okay, so you notice that this form is very similar to this form. Okay, so you can do the same for the third term. So that's p z times derivative with respect to y of x divided by x squared plus y squared plus z squared to 3/2. So this is pz x times negative 3/2 2z over x squared plus y squared plus c squared to the 5/2, which is equal to negative pz times 3x z over r to the 5th. Okay, so again, I expect you to just fill in the missing algebra steps. Okay, so therefore the force exerted by Q in the x component, which is Fx, and this is equal to this plus this plus this, okay, times this one. So this is Q over 4 pi epsilon times px over r cubed minus 3x over r to the fifth pxx minus 3x over r to the fifth pyy and minus 3x over r to the fifth pzz, which gives us this form. So Fx is equal to Q over 4 pi epsilon naught times Px over r to the fifth minus 3x over r to the fifth times Pxx minus plus Pyy plus Pzz. Okay, as you will notice, this term this whole term is actually P dot R. Okay, so from here we can assemble the rest of the terms. We'll have Fy, which will follow the same form, wherein Fy is equal to Q over 4 pi epsilon naught times Py over r cubed minus 3y over r to the fifth times Px plus Pyy plus Pzz. And Fg would be 1 of Q over 4 pi epsilon sub 0 times Pz over r cubed minus 3y over r to the fifth 3z over r to the fifth times Pxx plus Pyy plus Pzz. Okay, so these three terms will combine as this one, F, which is equal to Q over 4 pi epsilon naught times P vector, because this if you're going to make this a vector, you just add x hat, y hat, and z hat here. Okay, so this is Px x hat plus Py y hat plus Pz z hat is just P. And then their common factor is 1 over r cubed. And then minus 3x x hat plus 3y y hat plus 3z z hat, which is 3r. And then this is common factor, that's P dot r divided by r to the fifth. Okay, so again we know that r is equal to r hat. So this means that this term here, 3r p dot r is actually equal to 3r r hat times p dot r r hat. So when we divide this by r to the fifth, okay, so this is r, these are scalar quantities, divided by r to the fifth is r to the r cubed, which is common here. So finally, the final form of the force is q over 4 pi epsilon r cubed times p minus 3 times p dot r hat. Okay, so this is the force exerted by the charge q on your dipole moment, or on your dipole. Okay, so okay, if we're going to recall again, our second problem is that we want to calculate the force on Q. Okay, so we need to know the electric field due to your dipole. And from problem 3.36 of your book, the electric field due to a dipole is, in this case, r prime is equal to 1 over 4 pi epsilon sub 0 times 1 over r. So you will notice that r is equal to r prime, so just write in here r times 3 times p dot r hat prime minus r hat prime minus p. Okay, so let me just clean this up. Again, this is r prime. So we know already that r hat is equal to negative r hat prime, or r hat prime is equal to negative r hat. Okay, so that means you can rewrite this as 1 over 4 pi epsilon naught times 1, sorry, this should be r cubed. So that's 1 over r cubed times 3 times p dot negative r hat times negative r hat minus p, which is 1 over 4 pi epsilon sub 0 times 1 over r cubed times 3 p dot r hat minus p. And what do you notice here? So you will notice there that, okay, the force, if we're going to calculate the force, you just multiply this by Q. So this is electric field. Want to find the force, you just multiply this by Q. Okay, so you will notice here that, okay, let me rearrange here, that this term is actually the negative of this term. You see? Okay, so if we're going to call this FQ, let's call this FD, the force due to your dipole. So in other words, this is negative FQ. And what does this entail? It shows that the force exerted by Q on your dipole and the force exerted by your dipole on Q are actually action-reaction forces. And we already expect this by virtue of Newton's third law of motion. Okay? Easy, right? Quite long, but it's easy to understand. Okay? So this ends our discussion on problem 4.9 of your textbook. I hope you learned something today. And thank you guys for watching. I'll see you again in the next video. Bye-bye.